This is a cellular automaton explored by Rudi Rucker. We met it in video 3, 6 ideas. It's particularly useful because it's two-dimensional, with one space and one time dimension, giving it better visual appeal. While the most famous cellular automaton is Conway's Game of Life, with two space and one time dimensions, this uses cells with binary states and has been inspired by bacterial cultures growing in petri dishes. We prefer vectors because they can represent both magnitude and direction, making them more suitable for describing physical quantities. More importantly, this cellular automaton introduces a key concept that we'll need later: non-immediate predecessors. These are values from more than one generation ago that influence the current state. In Rucker's cellular automaton, each cell A contains a two-dimensional vector with three predecessors. Let's call them B, C, and D. The formula is simple: A equals B plus C minus D. We supply the first two rows of vectors shown in red, and the rest is calculated from them. Each row represents a generation. Think of this as our time axis. In our last video, we discussed how mathematical functions can be expressed as cellular automata. Interestingly, the reverse also works here. We can express this cellular automaton as a complex function. This is important because it shows that we can move between different mathematical descriptions while preserving the essential behavior. The value v of p at point P is v of p equals v of p minus 1 plus v of p minus I minus v of p minus 1 minus I, where all values are complex numbers. We will maintain this principle of using the same number sets for both values and coordinates, even for the ultimate generating formula we aim to present in this video series. V of p minus 1 and v of p minus I are immediate predecessors, but the third term is a non-immediate predecessor 2 generations removed from p. We also need an initial condition, defining the value at the origin and along the axes. Let's leave that for now and look at patterns quite far from the origin, assuming something interesting. As each generation depends on points from the previous generation, time and space run at 45 degrees in the grid, as we discussed in video 5. Let's rotate this so that time runs upwards, giving us the same layout as our original cellular automaton. By setting the vectors in the first two rows, we can get some interesting patterns that look like magnetic field lines. You can even get patterns that pass through each other. It's surprising to see this behavior from such a simple generating function, but we can make it even simpler. The current generating formula is adding two numbers and subtracting one number. What happens when we remove the non-immediate predecessors? Hang on, you say, but that means the vectors keep growing at a constant rate. That's true, but so what? As an analogy, imagine if everything in our world suddenly doubled in size. As long as the physical laws are adjusted accordingly, you would not notice. The object you measure and the ruler to measure it with both doubled in size, so no change relative to each other. You would, however, notice the doubling if you found an object not affected by it or less affected by it, like this coffee cup. Similarly, if the vectors that make up our world keep growing at a predictable rate, we wouldn't notice. Now, the Rudi Rucker function is also interesting without the third term. It looks messy with growing vectors, but if we scale the vectors down by multiplying with a half, we see that there's still interesting patterns. F equals a half, we call that a normalization factor. This is not part of the formula. Here is a curve with a linear scale, and here's the same curve on a logarithmic scale. The log is not part of the function, just a way to visualize it better. The same applies to our normalization. Let's deal with one possible objection first. It seems wasteful in resources if you look at this as a cellular automaton that needs to run on some hardware. If the numbers double each generation, we'll end up with huge integers requiring unrealistic amounts of memory to store. But this is just abstract maths, not something to run on a computer efficiently. Our assertion is that the universe is a finite grid with each point containing a finite vector. Very large, yes, but not infinite. Bear in mind that the traditional view is that space and time are continuous and filled with continuous fields of real number values. One single real number contains infinitely more information than an entire finite universe. At this stage, we could talk a bit about the difference between a state calculation and solving an equation. In traditional physics, we write equations that describe behavior and expect nature to find values that satisfy these equations. The Navier-Stokes equations are a perfect example of this approach. These equations describe how fluids move, everything from water flowing in a river to air moving around an aircraft wing. They're relatively simple to write down, but finding solutions is famously difficult. In fact, there's $1 million prize for proving whether solutions always exist in 3 space and 1 time dimensions. Think about that for a moment. We write equations that we ourselves have trouble to solve, yet expect nature to somehow find solutions to them in real time. Contrast this with our approach. Here, space simply calculates the next state from the previous one using basic integer operations. No complicated mathematics, no equation solving, just straightforward calculation steps. Konrad Zuse captured this beautifully with his term rechnender Raum, space that calculates, space which doesn't solve equations but calculates states. We expect that the rules that are normally considered fundamental physical laws turn out to be emergent properties. This is the 13th video in this series, but you might not recall all the previous videos, so let's recap a few points. In video 4, we defined a new multidimensional number set. It is modeled on the complex numbers. In fact, complex numbers are a subset of them. The key idea is that each order introduces new rotational constants, and these orders naturally create a hierarchy of dimensions. We defined one special constant per integer order, which defines how many multiplications are required to loop back to itself, and we call these rotational constants. The rotational constant order 1 is 1. Multiplying any non-zero number with 1 goes on a one-step hop to itself. The rotational constant for order 2 is -1. It takes 2 steps to return to the original state. Order 2 is a special case because it relates to the inverse of addition, so it doesn't generate a new dimension. We call the rotational constant for order 3 j. This is a new concept in maths. This allows us to express 3-dimensional numbers of the form a plus jb plus j squared c. The rotational constant for order 4 is the familiar imaginary number I, and we know the general form of complex numbers to be a plus ib. If we build the dimensions cumulatively, together with previous orders, we can express 6-dimensional numbers. The general form is a plus jb plus j squared c plus id plus ije plus ij squared f. We've conjectured that this number hierarchy has a deep connection to physics. As we said earlier, at each order the number system defines the coordinates as well as the values at each coordinate. So at order 4 we have a 6-dimensional grid, and each point has a 6-dimensional vector. The 6D grid gives rise to 3 space dimensions and 3 time dimensions, as we've shown in previous videos. Can you guess what the physical significance of the 6D values at each point is? I'll tell you at the end of the video. We've also conjectured that the order 3 rotations are connected to strong force interactions. These J operations allow us to define a 3-way symmetry that is absent but needed in physics. Currently the colors red, green, blue and anti-red, anti-green, anti-blue are used for that. This is weird because most other particle properties are expressed as numbers. The order 4 rotations are connected to electromagnetism. It is well known that complex numbers are required in theories that describe electromagnetism, like Maxwell's equations as well as QED. Order 5 gives us 5 extra dimensions, so now we're at 30. Not only do we have multiple time dimensions, but also a hierarchy of progressively weaker ones. Note that this was just a recap to jog your memory. If this is confusing, the previous videos explain all this less hurriedly. We can tell a time dimension because of the complexity gradient, the rate at which patterns in successive spaces become more intricate. As we'll see, this gradient varies with order. Along the 3 order 4 time dimensions, the complexity gradient changes much faster than along the 5 dimensions of order 5 and 6. But how does such a complexity gradient come about? If we see the set of spaces all with the same condition, why is the change slower for the higher ordered time dimensions? In previous videos, we only defined immediate predecessors. Now let's invent some non-immediate predecessors similar to the Rudy-Roche function, but for 6 and 30 dimensions, and make an estimate of their effect. Just like the coffee cup in our size analogy, the non-immediate predecessors are all less affected by the scaling and are therefore smaller. Note that this is just an example with some arbitrary definitions. The real situation is a bit more complicated, and we will revisit this in a later video, but it is instructive to be able to make some rough quantitative calculations now. The first arbitrary assumption we make for 6 dimensions are that the vector lengths double each step, and that the first non-immediate predecessor of p is 6 steps away at this coordinate. Therefore, after 6 steps, the immediate predecessors have grown by a factor of 2 to the 6 equals 64. So this order 4 non-immediate predecessor is about 1/64th of a size. This is only approximate because we don't know if the vectors align or are subtracted or are at right angles to each other. So if we're using this formula to calculate the value of the vector at p from the values of the 6 immediate predecessors and the 1 non-immediate predecessor, then the latter has much less influence since it is 64 times smaller than the immediate predecessors. At order 5 we get 30 dimensions because order 5 combines 5 sets of 6-dimensional numbers. This follows the dimension hierarchy we defined in video 4, where we reimagined imaginary numbers. We only invent non-immediate predecessors for non-prime orders, so all we have here are 5 copies of our 6-dimensional grid. For order 5, let's say we increase the lengths of the vectors by a factor of 10 each step. What effect does that have on the calculation we just made? None at all, because the ratio between them doesn't change. The immediate predecessors have 10 times longer vectors, but so do all the non-immediate predecessors. At order 6, we get no new dimensions. We're still at 30. However, order 6 isn't a prime number. When we have non-prime orders, we'll use non-immediate predecessors corresponding to each divisor of that order. So order 6 has 2 types of non-immediate predecessors because 6 is divisible by both 2 and 3. There are 3 predecessors that are 10 steps removed from p, and 1 more predecessor that's a whopping 30 steps away. However, for these order 6 non-immediate predecessors, the extra factor of 10 has an effect. For the 3 non-immediate predecessors that are 10 steps away, that means that they're about 20 to the 10, which is 10 to the 13 times smaller. And the one that's 30 steps away is 20 to the 30 times smaller. Let's summarize these first 4 values. If immediate predecessors are about 1, then order 4 is 64 times weaker, and order 6 are 10 to the 13 and 10 to the 39 times weaker. The higher orders in our number system not only add dimensions, but also introduce weaker time dimensions. Why weaker? Because the non-immediate predecessors at higher orders are affected by more steps of scaling, making their influence progressively smaller. It's similar to our coffee cup analogy. The further removed a predecessor is, the less it affects the current state. The progression of dimensions follows this pattern. Order 4 gives us 6 dimensions and 1 interaction via a non-immediate predecessor. Order 5 multiplies this by 5, giving 30 dimensions. Order 6 maintains these 30 dimensions, but adds 2 weaker interactions. Order 7 gives us 7 copies of the 30-dimensional grid. Order 8 doubles this to 420 dimensions, with 2 new sets of even weaker interactions. Now, the relative strengths we calculated match the observed strengths of nature's fundamental forces remarkably well. In video 3, we talked about hierarchies of forces and promised to complete the last column of this table. Here are the combined numbers. Gravity deserves its own video, but of course the hierarchy doesn't stop at 30 dimensions. At order 7, we just get 7 copies of the 30-dimensional grid, similar to prime order 5. But at order 8, we actually double the number of dimensions to 420, and we get 2 more sets of non-immediate predecessors. To the astromonders in the audience, is there any evidence for forces even weaker than gravity that drop off linearly with distance and not with its square? So it looks like we were able to make this fit the force strengths accurate to an order of magnitude by making some arbitrary seeming choices. We'll get back to this in a future video. The points we are trying to make here are that the non-immediate predecessors are responsible for the complexity gradient in our hierarchy of time dimensions, and that their rapidly decreasing effect are a possible explanation for the hierarchy problem of force strengths. Yes, I promised to say a word about the physical significance of the 6D vectors. Say we have a value v at a point in the order 4 grid where v equals a plus jb plus j squared c plus id plus ije plus ij squared f. We can look at this either as a single 6-dimensional vector, or the sum of 6 1D vectors, or 3 complex numbers. But the most natural way, given the hierarchical definition of the orders, is as 2 3D vectors. Let's say E equals a plus jb plus j squared c, and b equals d plus je plus j squared f. Then v equals e plus ib. The 3D vectors E and B are the electric and magnetic field vectors respectively. As you can see, the 6-dimensional order 4 has an obvious connection to electromagnetism. The electromagnetic field is 6-dimensional in a way that exactly matches our number system. Thanks for your attention.